Okay, so let's continue. So the programming principles are not something that will break everything you know. So you have the programming model. Then means that you have the parallelism you can extract from your application. Then you have the GPU, CPU partitioning, understand what you want to run on the GPU and what you want to run on the CPU. And the most important part beneath that is the memory and data management. So even if we have memory currency on this system, which allows to get a lot of additional benefits from the GPUs, we have to keep in mind that there is always a cost to transfer data between one compute unit and one other. So it will be transparent, it will be more efficient on AC92, but sometimes it's not worth to put a part of code on the GPU because the data will be located on the CPU and the cost to transfer data will be too expensive. And on the other hand, sometimes it's worth to do a small serial part on the GPU because the data are already located on the GPU. So that's something that is really important to keep in mind when when optimizing application. The key point is really to understand where the data is. So we talk about parallelism, and usually we think about compute parallelism, but now the issue is becoming more a data parallelism. So again, so we have this software threads correspond to a Scala processor, a thread block to a multiprocessor, and the grid will run on devices. So CUDA block, just to fix the naming convention, a function that runs on the GPU is called a kernel. Each block, each part invocation of function on the of a function running on the GPU is called a block. So a block is similar to a cage, and to have your grid, you would put a lot of cages on your device. And so that's for the convention. And you can have multiple kind of cages that would run on different grid, so devices. Now, going with the analogy with cages, a thread is similar to a hamster. So you will have to build a lot of them to integrate a lot of threads, a lot of hamster into your block. And each of them is recognized by thread ID. And the total number of threads that you have per block is the dimension of the block. So the difference between thread and block, so it's important to know, and then later understand how you will share or you will split the different parts. The threads are running on the same SM, so the communication is very quick. So it's similar to running on the same CPU core, CPU socket. Sorry, but then you also need to break into block because one block will run on a single SM. So the SM, you have 80 SM per V100, so you need to build a lot of them. And it will allow you to fully utilize and and use the GPU. One thing that is very that has been very problematic. I don't know if Nvidia has changed that in newer version of CUDA, but when you run Nvidia SMI, you see the occupancy of the GPU, but it's a wrong metric to look at, because actually what we have been told is that this occupancy is based on the occupancy of the SM, the first SM. So if you have only one block that is running and fully using the first SM, you can think that you are using 100% of the GPU, but actually you are only using 1 out of 80 of the GPU. So the best metric to use to see the use of your GPU is to check the power consumption. So if you have only 60 watts, 70 watts of power consumption, you are not using a lot your GPU. But if you start to get to 150, 200, you have a very good use of GPU. So that's something to remember about the GPU that I forgot to mention. So yeah, you will put a lot of block on different GPUs. Each block will use thread to run on the application. Keeping with the analogy, a GPU is a pet store where you have a lot of simultaneous multiprocessors. So it's a section of the store. So each SM can have 32 blocks that will be swapped one after each other. It can be of different type. So that's where MPS also helps. And on these cages, you can put a different number of threads, different number of blocks. Sorry. So it's important to really think about the number of threads and blocks, and usually it requires some testing, runtime testing, to figure out the best configuration, how many cages we will have, how many we'll put, so everything is running properly. And then on the SM and the GPU, we have a lot of different stuff running. So quick example, here we have a traditional SOXP kernel. So the global function, so it's written in CUDA. The global directive means that it's a function that will run on the device, but that can be called from can and will be called from the CPU. So to identify myself, so the I and the portion of the problem I have to solve, I use this traditional method, block IDX. So my block ID versus the block dimension plus my thread ID. It gives me my place in the grid I have to compute, and then I do the computation of the SOXP on my specific unit. So we see here that all the loop that would be for I 0 to n has been replaced by a simple function, and each of the threads will identify itself and run one part of the loop, in short. So here we have put 3 blocks, a block of 3 threads, and there will be some threads that will be unused. if we take the example of running 30 data elements with 10 threads per block, which is already suboptimal, but so if we split in 3 blocks of 10 threads, so one block will have the dimension of 10. So we'll have our first array here running on the first SM, the second array running 10 to 19, and the third running 20 to 29. So we see here that we'll have only 3 SM used per GPUs. So the expected occupancy will be very little. So the purpose also for GPU is to handle very large amount of data. So usually, depending on the algorithm, you need to figure out the bytes required on the flop to understand if it's something that is worth to move to GPUs. Now to program GPUs, there are always the 3 possibilities, same as for any optimization. You have either use of libraries that is preferred, but cannot be that trivial to use. You have the compiler directives, so you can put Pragma, OpenACC, or Openmp to instruct the compiler to do specific stuff. Or you can use specific programming language, so CUDA for GPU or assembly code for CPU. But for portability, it's not advised to use this programming language. I'll show you an example where we had to do it to get optimal performance. But again, it was a decision that was made carefully before going there. So the Nvidia libraries that are available, so there start to be a lot. So they're all on the chart. So QDNN for the neural network, Thrust to be integrated with C++ application, AMGX, that is an optimized version of PTC in short. So you have a lot of libraries that you can already use in your application. Yeah, very quickly, it's an example for OpenACC directives. So you don't change your code if the compiler don't understand the directive, the OpenACC directive. It will simply interpret that as comments. So it's something that is easy to use. With all editors, it's also highlighted specifically. So it's something that is easy to use and that does not break your code usually. I come back to that a little bit later. So that's something that now is working properly. So 6 years ago, I would have said that it's prototyping and you have to believe in what's happening next in the compilers. But now either OpenACC or Openmp are efficient to run application, to run directives. So here, typically the directive instructs data movement. So we are moving, we say that on the following kernel, we have to copy the data from A and B, and that will move back C. So if you don't put that pragma, both A, B, and C would be copied in and back, but you don't need to move an empty array to the GPU first, and you don't need to have the answer back. So putting that pragma already helps you cutting by half the memory bandwidth, the bandwidth that you need with the GPU. Then you instruct you tell the compiler that you will build a kernel, and then you explain that you want to do loop with gang. So gang is the equivalent of block, and it will do the proper optimization. You can add additional stuff to optimize later, but usually this is really the three first pragma that we use for code, and then we do what do we say? We use profiler to understand what's happening in the code, and given what's happening, we do some additional tweaking. So OpenMP works similarly. So instead of gangs, you have teams, but it's the same. So yeah, after I think you are more familiar than I with all this this pragma. You put pragma distribute before your loop, and you say that this is what you want to do parallelization for. On, sorry. So the device initialize a team, and then within the team you will distribute the workload. Sorry, it will distribute the workload across the teams, and then on the parallel 4 you will do your loop with different threads, and at the end you get similar results. You get a synchronization like CPU OpenMP, and you come back to serial part of code with a single array. So it's explained. So the one part for the of CUDA is that you have a lot of flexibility. You can do whatever you want on your GPU. So it's as a start to understand how the GPU works. It's quite easy to use, but as soon as you go to very large code, it gets a lot harder to maintain. So here we see that, sorry, translating a CPU SAXP to SAXP running on the GPU will be very easy. So you replace the loop by identifying your place on the grid, and you run the computation. The core of CUDA kernel is a little bit different. It's similar to C++ calling. But that's the only difference. So memory management is one of the key issue with using accelerators. That's what makes good life for non-hybrid homogeneous cluster. It's easier to do because you don't have to think about what you are doing with your data. So if you do explicit control with traditional CUDA code, you will have to allocate an array, then to copy the data that you want from the host to the device. Then you call your function, and at the end you do another call to memcopy to retrieve the data, and then you free your pointer. So that's something that's very hard to do, and that's what Nvidia has been working on. So before going there, you can do the same thing with the pragma. So using data pragma. So that's mostly what OpenMP4 and OpenACC have brought to directives. It's the management of data. And here you have the same, the equivalent as the CUDA code with OpenACC. Now, with unified memory that has been introduced, I think it was with CUDA 9, at least for 9, you don't need to manage the data anymore. The code, when it's compiled, will and at runtime will detect when a data is required, and will move it to a GPU. So the only thing that you need to do before, at least it was one of the drawback at first, is to think about synchronizing the data after the GPU function, the GPU call, because it was not automatic to move back the data to CPU. Sometimes we had some strange behavior. So with unified memory, it's much more easier to manage data. So you don't have to create anything on the device. You directly call your function, and you don't care about anything else. Still, it's good to help the compiler with pragma. Typically, the order of data transfer that you do to make sure that you overlap in the appropriate order. So that's another tweaking. Yeah, good point. Here, the GPU function call is non-blocking. So if you don't call the CUDA device synchronize, it won't wait for the GPU function to complete before going further. Yeah, that's the reason. So unified memory is, I think, is really helpful because you just need to focus on the compute part at first. When you run the profiler, and we'll get an example later, you can figure out if there are some more optimization you can do on the data migration. But usually what we want first to figure out is if the kernel is actually running faster on the GPU than it was running on the GPU. So it allows to get much easier use and porting time to GPUs. So the fundamentals, I will go quickly. It's more for reference. You will have the slides. Sorry, it's going down. Yeah. So it can be migration for CPU and GPU or CPU. It would be the same. So that's why we only call processor A and processor B. So here we have two memories that should be identical in the cache, in the local cache. So each time something is addressed or written, we call dirty page on the other side, and when it's accessed on the other side, there is a page migration that is requested. So we will always have the good information on the memory. What is and memory over subscription works in the same. So when a page is not good anymore, when we need more space, sorry, we will move the page to another place and retrieve the memory that we want. I don't recall this one. Yeah, so when there are concurrent access, it's always the last one that will get the last word. So that's something that must be taken care of. I don't recall. Yeah, sorry, I recall. So the drawback of unified memory is that if you are mistakenly accessing the same memory at the two place, so typically you do computation on GPU and you do some computation, some writing specifically on the CPU. It will call data transfer, and you will lose a lot of latency on cycle. So the important part is to be sure that you don't do too much operation on the data that has been moved to the other side. So that's something important to recall. And QDAS to use memory, to use the unified memory in CUDA-C, there is something that is called a CUDA malloc manage. So it's an extension of malloc that will ensure it's considered in the unified memory space. In CUDA Fortran, it's the attribute manage that is used. And when you compile your code, you need to add the target managed plus the GPU architecture that you want to the options, so that you have all dynamic allocation declared as managed. So with Openmp 5, it will be there soon. And usually what is done is to write its own malloc hook to intercept all the call to malloc and to use them as a CUDA malloc manage. That's a standard trick to use managed memory in existing code. We go quickly about that. So the profiler, you might know NVProf, note it's Nvidia Insights. So they are about the same look and feel. It's a tool that is very important to understand where you are spending time. So here there are some example. Quickly. One good point is that you can filter on specific events that you want to check, and you can also correlate call runtime results with your code. Sorry. Sorry. So you can quickly figure out where you are spending most of the time. So in this example, we would check each brown bar to understand where this transfer is happening and why. And usually what you want to do is to pack all of the transfer together. And similarly to Pragma, you can also provide some some hint to CUDA so we can at runtime better schedule all the memory movement. Oh, sorry, I should have moved that away. So again, unified memory is a good way to very quickly have a code running on GPU because you don't take into account, you don't move the data by yourself. So everything that is non-trivial is covered by the managed memory. Usually it's good enough also in terms of performance. But again, after coming back with the profiler, you also have the capability to come back and to instruct, to provide more hints to your application, either still using unified memory or starting to implement direct memory management in your application. So there are a lot of additional resources that I put there if you want to learn more about GPUs, especially the Quick Lab. You have a lot of training about CUDA and OpenACC that can be found there.